Have you ever heard of a frog battery? It might sound like something out of a science fiction story, but it's a real device from the early days of electricity research. A frog battery is an electrochemical battery made by connecting dead or sometimes even live frogs in series, using their muscles as the cells of the battery. This unusual biobattery was used in scientific investigations and academic demonstrations to explore the mysterious world of electricity. Back in the 18th and 19th centuries, scientists didn't fully understand how it worked, but they knew that damaging a frog's muscle created an electric potential. This injury potential became the basis for the frog battery, sparking curiosity and debate among early researchers. The principle behind the frog battery is known as the injury potential or demarcation potential. When a muscle is damaged, it creates a small electric potential. In the 18th and 19th centuries, scientists didn't fully grasp this concept, but they observed that dissecting frog muscles generated electricity. This effect is now understood as the result of increased electric potential due to injury. The frog battery is just one example of biobatteries, a class of batteries that use animal tissue to generate electricity. The general term for these is the muscular pile, and they can be made from various animals, not just frogs. The first well-known frog battery was created by Carlo Matteucci in 1845, but he wasn't the only one experimenting with animal electricity. Earlier, Eusebio Valli built a chain of 10 frogs in the 1790s, though his work was overshadowed by debates about the true nature of electricity. Leopoldo Nobili in 1818 constructed a frog pile using complete frog legs, while Giovanni Aldini demonstrated that even ox heads could serve as battery components. These early inventors were driven by curiosity and a desire to understand the mysterious forces of electricity, often using whatever animal materials were available to them. In the early days of electrical research, frogs were a common sight in laboratories. Their legs were especially sensitive to electric current, making them ideal for detecting electrical signals. Researchers kept a steady supply of live frogs ready to prepare their legs for use in galvanoscopes, devices that detected electric current. Frogs were small, easy to handle, and their muscles responded longer than those of other animals. This made them not only convenient but also effective for a wide range of experiments, including the construction of frog batteries. To build a frog battery, scientists typically use the thighs of frogs. The process began by skinning the legs, cutting off the lower part at the knee, and carefully slicing the thigh muscle in half. Only the lower conical-shaped piece was kept for the battery. These half-thighs were then arranged on an insulating surface, such as varnished wood, so that the inside surface of one touched the outside surface of the next. The ends of the pile were placed in cups of water, which acted as the battery terminals. This arrangement was based on the belief that electricity flowed from the inside to the outside of the muscle, though we now know the real source was the injury potential. The frog battery is a specific example of a broader class of biobatteries known as muscular piles. These devices can be constructed from various animal tissues, not just frogs. For example, Aldini used ox heads and Matteucci experimented with eels, pigeons, and rabbits. The key idea is that animal muscle, when injured or freshly prepared, can generate a small electric current. This discovery opened up new possibilities for understanding bioelectricity and inspired further research into how living tissues interact with electrical phenomena. The history of the frog battery is filled with scientific debates. Eusebio Valli believed that animal electricity was different from the electricity produced by metals, while Alessandro Volta argued that the real source was the metals themselves, with animal fluids acting only as electrolytes. Volta's invention of the voltaic pile, which used only metals and no animal material, eventually proved his theory correct. Despite this, the frog battery remained an important tool for exploring the mysteries of electricity and helped lay the groundwork for modern bioelectric research. Let's take a closer look at how a frog battery is constructed. The half-thighs are carefully arranged in series, with each inside surface touching the outside surface of the next. The conical ends fit into the cavities of the cut surfaces, and the entire pile is placed on an insulating base. Cups of water at each end serve as the battery's terminals. This setup was believed to create a continuous flow of electricity, though we now know it was the injury potential at work. The careful preparation and arrangement were crucial for generating a measurable electric current. Although the frog battery is now a historical curiosity, its legacy lives on in the field of bioelectricity. These early experiments helped scientists understand the electrical properties of living tissues and paved the way for modern research in neuroscience and physiology. The debates and discoveries surrounding the frog battery also highlight the importance of questioning assumptions and testing new ideas. Today, the story of the frog battery reminds us of the creativity and persistence of early scientists and how even the most unusual experiments can lead to important breakthroughs.